Okay, these are going to be our notes about the mean value theorem. The mean value theorem is one of those theorems that is actually very important in calculus, but it's kind of a behind-the-scenes theorem. It's actually used to prove a lot of the ideas that we use when looking at applications of derivatives. So while it may not have an obvious place in calculus when you first take your entry-level calculus courses, it's actually the backbone of many of the ideas that we use throughout the course. Before we actually talk about the mean value theorem, we start with a different theorem. We start with a theorem called Rolle's theorem. And Rolle's theorem says the following. Suppose f is a function that meets the following conditions. F has to be continuous on the closed interval AB. So notice the brackets instead of parentheses. That means that it has to be continuous on the endpoints of this interval as well. Now the second requirement is that the function has to be differentiable, that is, the derivative has to exist on the open interval from A to B. So it only has to be differentiable everywhere except the endpoints. And remember, the things that make your function not differentiable are things like discontinuities, sharp changes in direction, or vertical tangents. And then the third requirement for Rolle's theorem is that f of A has to be equal to f of B. And what that means is that when you plug A into your function, that being your left endpoint, and when you plug B into your function, that being your right endpoint, the y values that you get in both of those cases have to be the same. If you have a function that meets all three of those conditions, then your conclusion is there has to be some number c in AB, and if c is in AB, that means it's somewhere in between them, and since those are x values, that means c is also an x value. So there's some x value on that interval such that when you plug that x value into the derivative of your function, you're guaranteed to get 0 at least once. So let's take a look at three quick examples. I've got these kind of set up for us. The interval goes from A to B on each one of these, and I've already set these graphs up to meet that third condition, that the y value for A and the y value associated with B have to be the same. So what I'm going to do is on each one of these draw a different continuous and differentiable function on the interval. So for example, here is one thing that this graph could look like. Here is another thing this graph could look like. And then here is a third thing. These are by no means the only three options, but I just wanted to give you a couple different looks of what these kinds of graphs can look like. So as long as you have any kind of continuous and differentiable function in between these y values, you're guaranteed at least once to find a number c where the derivative is equal to 0. So graphically, that means, for example, over here, your derivative is positive, positive, positive. Sure enough, right about here, you're going to get a derivative that's equal to 0. So that would be my c in this case. Here, we've got a positive derivative, and then right here, it's going to turn to 0. So there is one place, but actually in this particular example, there's a second place on my interval where my derivative would be equal to 0, right here. So we can call that c sub 1 and c sub 2. The idea is you're guaranteed at least one. So this one, where I actually drew a line in between the two, not only do I have one place where the derivative is equal to 0, the derivative is equal to 0 everywhere in between a and b, if this is a constant function. So there are other things this graph can look like, obviously, but this is the basic idea behind Rolle's theorem. If we wanted to take a look at a quick example on working with these algebraically, let's say we wanted to verify that the function satisfies the conditions of Rolle's theorem, and then find all numbers c that satisfy the conclusion for f of x equals x cubed minus x squared minus 6x plus 2 on the interval from 0 to 3. Okay, so notice the wording of the question. If this were, for example, a test question, it's not that you have to have Rolle's theorem memorized word for word, but if you don't know the conditions of Rolle's theorem and the conclusion of Rolle's theorem, you can't answer this question. So I will never ask you to rote memorize a theorem, but you do need to know generally what are the conditions and what are the conclusions for things like this. So the conditions, it's got to be continuous and differentiable on 0, 3. Now this one's a little nice because if you take a look at this function, the classification of this function, this is a polynomial. And because of that, polynomials are continuous and differentiable everywhere. So it's definitely continuous and differentiable on 0, 3. But we need to make that statement. So then once we've got that, we just need to verify the third requirement. The third requirement for this is that f of a has to equal f of b. A in this case is 0, so we need to find f of 0. That's the easy one. When you plug 0 in, you just get 2. When we plug in b, which is 3, f of 3 gives me 27 minus 9 minus 18 and plus 2. So 27 minus 9 is 18, minus 18 is 0, plus 2. Sure enough, it gives me 2. When I plug in 0, when I plug in 3, I get the same y value. And that is true in this case. If it weren't, Rolle's theorem would not apply. Once I've verified that I actually meet those conditions, I can check the conclusion. And remember, the conclusion is that the derivative at some number c, so that's f prime of c, is guaranteed to be equal to 0. And we need to figure out where that happens. Well, if you want to know when your derivative is equal to 0, we set it equal to 0. So we find the derivative of c, f prime at c. The only difference between f prime at c and f prime at x is instead of saying, for example, the derivative of x cubed would be 3x squared, it would be 3c squared. We have a c in place of x. So then minus 2c minus 6. And we want to set that equal to 0. Now, you can try all you want. This one does not factor. So if it doesn't factor, we need to go ahead and use quadratic formula. So that's c equals, that's 2 plus or minus the square root of 4 minus 4 times 3 times negative 6 all over 2 times 3. So when we do the arithmetic on that, we'll have 2 plus and minus the square root of, let's see, 24 times 3. 4 minus that'll give me 7. Actually, it'll be plus. It'll be that plus 4. So it'll be 2 plus and minus the square root of 76 over 6. And then this simplifies down. This is 4 times 19. So that's 2 square root 19. Divide 2 into everything. 1 plus and minus the square root of 19 over 3 once you divide 2 into everything. Okay, so it looks like we're done. We found 2 c values, but the trick is you want to make sure that these satisfy the conclusion, and the conclusion is that you're guaranteed a c on this interval, or somewhere in between 0 and 3. If you check the decimal representation of 1 plus and minus the square root of 19 over 3, the plus version gives you 1.78, and the minus version gives you negative 1.11. So we actually don't want to consider this one. It's not that it's not a solution to that quadratic, it is, but the conclusion of Rolle's theorem talks about numbers in between 0 and 3. So that's the only one we want to use. So we'll do c equals 1 plus the square root of 19 over all over 3. And that's our c. So once we've discussed Rolle's theorem, now we can talk about mean value theorem. And mean value theorem, when you read it, you'll kind of see why we start to talk about these at the same time. Suppose f is a function that meets the following conditions. F is continuous on AB, and f is differentiable on the open interval AB. So it's got the same first and second requirements for the function. It's got to be continuous on the closed interval, and it's got to be differentiable on the open interval. Notice the lack of the third requirement. You're no longer required to have f of a equal to f of b when you're talking about mean value theorem instead of Rolle's theorem. But of course that's going to change our conclusion. Okay? So the conclusion is now that there is a number c, and that number c is somewhere in between a and b. So c is some x value in between your left and right endpoints, such that the derivative at that c is now equal to f of b minus f of a over b minus a. So take a look at that, and it should look a little familiar. You see how in the numerator you have a y value minus a y value, and in the denominator you have an x value minus an x value? That's a slope equation. Specifically, it's the slope between the point associated with A and the point associated with B. Okay, so let's take a look at a quick picture of what some of these can look like before we discuss more about what this means. So let's take a look at these. I've started this out similarly. I put the axes on here, only this time when I drew A and B, they have different Y values, and it doesn't matter which one's bigger and which one's smaller. So for example, in the first graph, I've got f of A higher than f of B, and in the second one, I have f of A lower than f of B. It doesn't really matter. So I'm going to draw a couple of graphs. So I need them to be continuous and differentiable. That's my requirement. So here is a continuous and differentiable function, and let's say here is a continuous and differentiable function. So what this is going to talk about is at some number c, I'm going to have a derivative equal to the slope between the point here at A and the point here at B. Pictorially, what that looks like is that if you look at the slope between the endpoints, say here, at some point my derivative is going to have the same slope as this line right here. So in this particular case, it's a pretty bad drawing, but let's say it's right about here, give or take. That would be my C for this particular graph. The next one, look at the slope between the endpoints. The slope between the endpoints would be about this. So I'm looking for where would my derivative, where would my instantaneous rate of change be equal to this. So in this case, it would be right about here. How do I know they're the same? They're parallel. So there's one place, but this one would actually have a second place where it would also have a tangent line parallel to that secant line, say here. So there's two of them. So you're guaranteed one, but you can definitely have more than one. So to kind of put it back in terms of the first thing we learned about derivatives is that what mean value theorem guarantees is that the slope of the tangent line at some point has to be equal to the slope of the secant line between the endpoints. Also known as the average rate of change has to be equal to the instantaneous rate of change somewhere on that interval. And just a quick mention on notation. Sometimes when you see this written, you'll see this written slightly differently, the conclusion. They'll take the derivative of f at c times b minus a and say that's equal to f of b minus f of a. And notice these are the same thing, it's just the b minus a has been multiplied over times that f prime at c. This is actually the more common way to see the conclusion of mean value theorem written, but to me it makes it a little more obvious what it's describing if you can write it in this way instead. So you'll see them used interchangeably. Let's take a quick look at an example. Verify that the function satisfies the conditions of the mean value theorem. Then find all numbers c that satisfy the conclusion for f of x equals x cubed plus 2x squared minus x on negative 1, 2. So again, we need to address the conditions before we can apply the mean value theorem. Make sure you actually can apply the mean value theorem. And because this function is a polynomial, we're going to be able to write a similar statement to the one we did in the example for Rolle's theorem. F of x is a polynomial, it's therefore continuous and differentiable everywhere. So it's definitely continuous and differentiable on negative 1 to 2. Just for argument's sake, let's say that I had been given something like f of x equals 1 over, let's say, x minus 3. You could not say that that's a polynomial. It's not. It's a rational function, and it's not continuous and differentiable everywhere. It is, however, continuous and differentiable everywhere as long as it's not looking at 3. So let's say this were the interval I was given for this particular problem. The kind of statement I would need to write then is something along the lines of f of x is rational, and it is therefore continuous and differentiable everywhere except 3. And since 3 isn't on your interval, you would still be able to use mean value theorem. Okay, so that's how you'd handle it if it actually had a discontinuity. As long as it's not on the interval you're dealing with, you can still use mean value theorem or Rolle's theorem for that matter. Notice I don't have a third condition to check. F of negative 1 does not need to be equal to f of 2. So our conclusion then is that the derivative at some number c, and again remember f prime of c is pretty much the same thing as the derivative of f at x, it's just that we have c everywhere instead of x. So that will be 3c squared plus 4c minus 1. Okay. So once we have that, this time though you got to be careful. You're not setting this equal to 0. You've got to set it equal to the slope between the endpoints. Well, that means we need to calculate the slope between the endpoints. We need f of 2 minus f of negative 1 over 2 minus negative 1. Okay. So f of 2, we're going to get 8 plus 8 minus 2. So that's going to give me 14. Minus, when we plug in negative 1, we're going to get negative 1 plus 2 minus negative 1, which is plus 1. So that'll be minus 2 over, and then 2 minus negative 1 gives me 3. So that gives me 12 over 3 for 4. So that is what we're going to set our derivative equal to. We are guaranteed at least one time in between negative 1 and 2 that this derivative has to be equal to 4. If you want to know where it's equal to 4, set it equal to 4. So here we go. It's a quadratic. Everything to one side, 0 on the other side. So that's 3c squared plus 4c minus 5 equals 0. Again, this one does not factor. So that's going to be c equals quadratic formula. Negative 4 plus and minus the square root of, that's going to be 16 minus 4 times 3 times negative 5 all over 2 times 3. Okay. So again, this one's going to turn to a plus. We're going to get negative 4 plus and minus. Yeah, apparently I liked 76. That's 2 root 19 again, all over 6. So when we divide the 2 through, we're going to get negative 2 plus and minus the square root of 19 over 3. Okay. So once again, we need to give a quick check and check which one of those, they could both possibly be in the interval. We might end up keeping both of them as a solution. That's entirely possible. But as it turns out, only c equals negative 2 plus the square root of 19 divided by 3 is in the interval between negative 1 and 2. So that's the c that satisfies mean value theorem for this particular problem. So one of the interesting side notes about the relationship between Rolle's theorem and mean value theorem is Rolle's theorem is actually mean value theorem, but it's a specific case of the mean value theorem. So Rolle's theorem required that f of a be equal to f of b, right? That was the requirement that we took off when we're dealing with mean value theorem. Well, if you look at Rolle's theorem and you let f of a equal f of b, what is the slope between those endpoints? If you look at the slope between the endpoints, because they're the same, the slope between them has to be 0. Hence, Rolle's theorem is just a special case of mean value theorem. Let's take a look at one more example. Suppose that we know f of x is continuous and differentiable on the interval from 6 to 15. Let's also suppose that we know that f of 6 happens to be equal to negative 2, and we know that the derivative of f for all x is less than or equal to 10. What is the largest possible value for f of 15? So we know that the interval that we're working with, we have a left endpoint of 6 and a right endpoint of 15. We happen to know f of 6 in this particular problem, and we've got an upper bound for the derivative of f at x. We know it can't possibly get any larger than 10, at most 10. And we're trying to find out some information about the function's value at 15. So let me write down the conclusion of the mean value theorem real quick. This is its conclusion, assuming that your function is continuous and differentiable on your interval, which we have already been told that it is. So this is our conclusion. Our b is going to be 15, and our a is 6. Let's see what kind of pieces we can fill in for this. Okay? So f of b is going to be f of 15. F of a is f of 6, and then b is 15, and a is 6. And we know that the derivative at some number c has to be equal to this. Okay? And you're guaranteed that c falls somewhere in between 6 and 15. Okay, well, we know f of 15 is what we're trying to find information about. So we're just going to leave that as f of 15 for the moment. F of 6 we happen to know is -2. So that's minus -2. And of course 15 minus 6 is 9. So what we know is that the derivative at c has to be equal to this, but for any c, this derivative has to be less than or equal to 10. So this derivative will be less than or equal to 10. Notice if you just concentrate on this piece after the thought process, there's only one thing to solve for here, and that's f of 15. Well, that's what we're looking for information about. So we just finish it up. F of 15, this will be minus -2, which becomes plus 2. Divided by 9 has to be less than or equal to 10. This tells me that f of 15, if you multiply over by the 9, you get 90, and subtract the 2, you get 88. Must be less than or equal to 88. The largest possible value for f of 15 is 88. Not bad, considering you don't have that much information about this function. You're able to say that its value at 15 can't possibly be larger than 88. So that's mean value theorem.